Okay, right. So let's consider the following problem. Let f be a continuous function on closed AB. And AB are real numbers, A less than B. So we're going to just suppose that the integral from A to B of the absolute value of f of t dt equals 0. And then what do we have? Well, then f of t equals 0 for every t in AB. So it's the zero function. Now, before we actually go into this proof, we will quickly sketch a diagram because it's useful. So we'll just do the x-axis. It doesn't have to be very good. That's A, that's B, and we're just going to let some point, say x0, in this interval be such that f of x0 isn't 0, which means the absolute value of f of x0 has to be positive. And, f can be something weird maybe, like this. We don't actually know anything about it at the moment. We're just going to have a guess that it isn't 0, and then by contradiction prove it is. So because f is continuous, the absolute value of f is continuous as well, so you can pick a little region. We can pick a region here where the height is f of x0 divided by 2, and then these little regions are x0 plus delta, x0 minus delta, or some positive delta, which is probably going to be quite small. And then what we're actually interested in is this integral here is simply the area under the entire graph. And then this area we've just made here, the red box, this area is obviously going to be less than the entire green area. So, we can just say like this. This isn't a proof. This is just a sketch. That's going to be our argument. That this green area will be bigger than the red area. But the thing is, this thing here, this is going to be bigger than 0, obviously, because it has an area. Okay, right, let's get into the actual proof, keeping that diagram in mind. So, proof. Suppose for a contradiction that f of x0 is non-zero with some x0 in AB, and this is open. We're not going to deal with the close right now. We'll deal with that at the end. Now, the absolute value of f is a composition of two continuous functions. The first function being f, and then the absolute value. And that means the absolute value of f is also continuous. So let's just write that down. Absolute value is a composition of continuous functions, so is continuous. We can clearly see that the absolute value of f of x0 is greater than 0 because f of x0 isn't 0, and the absolute value is just going to be bigger. And since the absolute value of f is continuous, well, that's some terrible spelling, continuous, at x0, what do we know? We can pick a delta bigger than 0, so that's this delta here. such that, well, first of all, what we want to ensure is our region's actually inside the interval, because if it goes outside, it's not very helpful. We don't want to have our delta reaching all the way outside of B, so we'll just make sure it stays inside. And for x minus x naught less than delta, so we want x to be very close, or at least reasonably close to x naught. We have the size of the absolute value of f of x minus the size of f of x naught. We want that to be less than f of x naught over 2, absolute value of that. So that's just setting up this square for us to do stuff with. Now, if we unwrap this inequality, this is the same thing as this statement here, minus the absolute value of f of x naught over 2 is less than the thing above. And now if we add in this term to every single side, and then we're mainly interested in the left-hand inequality, so we add on this. So this is a 1 minus a half. So on the left we'll have absolute value of f of x naught divided by 2 is less than the absolute value of f of x. And again, this makes sense. We're just saying all these points that are in between x naught minus delta and x naught plus delta, they're just less than f of x naught over 2 absolute value. Okay, now we're ready to finish off the proof. So it follows that the integral from a to b of the absolute value of f of x dx, well, the integral over the entire, well, since the absolute value of f of x is positive, the integral over the entire domain is going to be bigger than just over our little interval that we picked. So we can do this. And now, because f of x, the absolute value of f of x is bigger than the absolute value of f of x naught over 2, in this region we can make another estimate. So we'll have x naught minus delta to x naught plus delta, absolute value of f of x naught over 2 dx. This here is constant, and we know how to integrate a constant function. We just evaluate the endpoints. This area is then just 2 delta, because that's the width of this interval, times by the height of the rectangle. And the 2's cancel away. So we're left with delta, absolute value of f of x naught. But delta is positive, and this term here is also positive, so this entire thing is positive. But that isn't 0 then, is it? It can't be both greater than 0 and also equal to, in this case, when this is a strict inequality. Right, so then, this is a contradiction. So f of x naught equals 0 for every x naught in open AB. And simply just by continuity, the endpoints also have to be 0. Otherwise we'd have to make some sort of jump. So we can't be 0 all the way along here. I shall do this in blue. We can't be 0 everywhere along here and then suddenly jump to something up here, because then it wouldn't be continuous anymore. And then what do we have? Well, on closed AB, f is identically 0. So f is the zero function, and we're done.